So you've got this complementarity property of quantum mechanics, and quantum mechanics is statistical in nature. Determinism goes out the door. Now I'll give you now an example on the second half of the board where you need to start thinking statistically. Now this rectangle here is a polarizer. I'll get some glasses here just a minute. These are ordinary reading glasses, but imagine they were sunglasses, and the glass here had like they were Polaroid sunglasses. So to stop the rays of strong sun getting into your eyes. Now, say the polarizing direction of these sunglasses, say vertical, so like this. So this is Polaroid sunglass glass, right? Imagine it's here. So if now light can be polarized in a certain plane. It can be like if you have polarized light in a certain vertical plane. So the light is oscillating like this, vertical plane. You can have horizontally polarized light. It can be oscillating this way, horizontally. Okay. So what a polarizer does, it blocks the light. It stops the light, absorbs the light, stops the light going through the polarized glass, depending on the angle of polarization of the light relative to the glass. So, for example, say so this glass, its polarization direction is vertical, and now let's say, well, say here, and now let's say some horizontally polarized light comes in this way, hits the glass. It will be absorbed totally, and no light will get through, because the angle between this vertical and this horizontal, here's the light, that is 90 degrees, and the fraction of the light getting through depends on the angle between the plane. Like if the light's coming in at say 45 degrees, so this vertical, so this is the plane of your light. Right? Say it's 45 degrees. So this angle here, 45 degrees. So half the light will go through. Okay? And this angle here, theta, between the vertical of your polarized glass, and the plane of the light, polarized light. So here's the plane that the light is oscillating in. Right? So let's say that angle here is 45. Half the light will go through. Now, if you decrease the angle, see this angle here is theta. More and more of the light will go through. So as your angle gets smaller and smaller until all of the light goes through. Now, what fraction of the light does go through? Well, cos squared theta. Right? That's you can measure that empirically. Do experiment, and you'll find that the proportion of the light going through will be cos squared theta. But now you have a deep conceptual, philosophical, interpretive problem, right? And this is what I'm leading up to. This is why I'm talking about this. Because now we're talking about photons, right? Now this kind of thinking is classical thinking. That's from Maxwell's time, looking on light as a quantized. Looking on light as continuously variable energy levels. Light can take on any energy levels. But if you start thinking in Einstein's terms, in terms of light bullets, bullet particles of light, photons, then photons come in discrete energies, right? You can't. Your photon exists or it doesn't. It's sort of like a bullet. It's there or it's not there. You don't have half a photon, Okay, so when a photon comes here, and does it go through the Polaroid glass or not? Now, if you have a lot of light going in, that just means lots of photons, right? So statistically, the proportion of them, the fraction of them that'll go through, will be cos squared theta, right? But now, imagine you only have one photon. Say you reduce the intensity of the light so that that it's so low that only one photon is going through per second, let's say. So what does that mean? How do you interpret, like, if you've just got one photon going in, does it, and let's say this angle here is 45 degrees, so does that mean like half the photon goes through and the other half gets absorbed? So you've got like a half a photon going through? No. What happens is, if you do the experiment, the photon will either go through totally or not go through at all. But the probability that it goes through is a half, if this angle's 45. Right? So it goes through or it doesn't. Now that's odd, right? So a photon goes through or it doesn't. So this leads to a kind of statistical thinking in quantum mechanics. So quantum mechanics, it's calculating quantities. I'm jumping ahead a little bit here. They're usually called amplitudes. Don't worry too much. But quantum mechanics, the rules of quantum mechanics allow you to calculate quantities that give you probabilities of something happening, but not. It doesn't describe the details of what's happening with just one thing. Now, my old prof, David Bohm, he was very unhappy with that. So were many others. I want to give you a famous list. Einstein hated quantum mechanics. Didn't like the underlying philosophical foundations of quantum mechanics. He was a determinist. He wanted to see quantum mechanics modified so that quantum mechanics plus something would allow, again, determinism. Who else? Schrödinger, famous name. That's the same Schrödinger's equation, famous name. He hated quantum mechanics. Well, he was one of the fathers of it, but he didn't like the lack of deterministic phenomena in quantum mechanics either. So let's see. So Einstein, de Broglie, Schrödinger, David Bohm, and others didn't like the statistical nature of quantum mechanics, right? So now, saying a bit earlier, classical physics is deterministic. You can determine with infinite precision the future or past state of a system by using knowledge of the state at one time, t1. You can predict with certainty what the state will be at some other time, t2, either in the future or in the past, using Newton's laws of mechanics, his famous three laws, right? But quantum physics is indeterministic. Like, I mean, what happens to the photon, the single photon? Does it go through or doesn't go through? Now, we've got the statistics. We know the probability of it going through is cos squared theta. But if you ask the question, well, what is that particular one photon, what's happening to it? Why does physics not have a theory that explains what's happening to that one photon? And that was David Bohm's point of view. And I personally was very attracted to that. I said, yeah, it'd be nice to maybe add some extra variables. They're called hidden variables because to quantum mechanics they're hidden. But wouldn't it be nice if you could add some further variables and create new laws that use those hidden variables, HV, in such a way that you end up with determinism again. So in a sense, amplify, modify quantum mechanics so that you've got determinism again. And that was what Einstein was really keen on seeing, but never saw it. We still don't have it today. In fact, well, I'm leading. I'll just give you the name. Toss this out. We'll definitely be doing this at higher levels, in graduate level. The name Bell, B-E-L-L. In the 60s, Bell started thinking hard about the foundations, the interpretation of quantum mechanics, and he came out with a famous test. He derived what are called Bell's inequalities, which allowed experimental physicists to go away and actually test between local, occurring within a small distance of something, local hidden variables, and quantum mechanics. You could actually, there was a difference. Bell derived some formula that predicted a difference between local hidden variable theories and quantum mechanics. And in the 80s, well, 70s and 80s, these experimental tests were done and quantum mechanics won. So that means that local hidden variable theories have been ruled out by experiment. And so what's left now are just non-local or entangled hidden variable theories. And what does that mean? What's going on in nature, that something that happens here in 0 time can influence what's happening here? Well, that's where we are at the moment, deeply puzzled, right? So if you're a physicist, you like math, and you have a philosophical turn of mind, then you may be fascinated by these questions, these deep questions. What the hell is going on in nature that this kind of thing can happen? But experiment has now ruled out local, hidden variable theories. So all we're left now with is non-local, entangled hidden variable theories. Maybe. All right. So to finish off a little bit, more puzzles, right? More weirdness coming from quantum mechanics. Now, you've probably heard the name Rutherford, famous name, a New Zealand British nuclear physicist. In fact, the nucleus was his term. He invented it. He's the father of nuclear physics. 1911, I think he was shooting alpha particles. His term again. Some journalist at some time asked Rutherford, oh, Lord Rutherford, why are you constantly riding the peak of the wave? Why was he so famous and always in the news all the time? And Rutherford's famous answer was, well, I made the wave, didn't I? Right? Anyway, so Rutherford shot alpha particles. What are they? They're helium nuclei, the helium atoms with the 2 electrons ripped off. So he was shooting these helium nuclei, alpha particles, at gold, very thin sheet of gold, and he expected these particles to just go straight through, and because he was testing the nature of the atom, trying to get a model for what atoms were like. Now he knew about the electrons. They were discovered a decade or 2 before, in the very late 1800s, and was very surprised when some of these alpha particles actually bounced back, and that deeply shocked him.